Hey there, this is going to be a screencast on some new material, and what I'm going to do today is move from talking about probabilities, because we have sort of touched on everything we need to touch on in our introduction, and I'm going to return us to random variables. And today I want to introduce a couple ways that we describe random variables. And so some of what I'm going to talk about relies on the handout I wrote up about random variables. So hopefully you've read that. If not, you can go back and take a look at it on your own time. So also, this conversation is leading us up to talking about some special classes of random variables. But here I want to talk about some more general ways that we talk about random variables. And specifically, we're going to talk about ways of describing a random variable's central tendency. Okay, and so we're going to talk about mean. And later, not today, we'll talk about median and mode. Those are probably terms that are reserved for statistics and samples. So mean is a way of us introducing the idea of central tendency. And then we're going to talk about how to describe the spread of a random variable. And I'll define the idea of variance. And that'll lead to the idea of standard deviation. Okay? So let's get going. So let's recall that given us a discrete random variable, and I'll abbreviate random variable for the rest of the day as RV. And let's call the random variable X. We can define a probability distribution Okay, we'll abbreviate that a PDF. Sometimes it's called a probability mass function. Our statistics text prefers that term. And it's the function p of x that's defined to be the probability the random variable takes on the value x. Okay. And then there's another associated function that we haven't talked too much about, called a cumulative distribution function. Or a CDF. That's defined by f of x is equal to the probability that our random variable's output is less than or equal to x. Right. So these are the main differences: an inequality for the cumulative distribution function and the inequality for the probability mass function. I want to point out that this definition is specific to a discrete random variable. If we go into a continuous random variable, we have to have a different definition, but I'll address that later. So just to refresh our memory, let me show you what a PDF would look like and a CDF would look like for the random variable x, which is the outcome of rolling a six-sided die. Okay, so in this case, our sample space are the numbers 1 through 6. And if the die is fair, then each outcome is equally likely. Oops. So then we'd say little p of x equals 1/6. The probability of rolling an x is 1/6 for every one of the x's in the sample space. So let's look at the cumulative distribution function. So the CDF for this would be a capital F of x, which is the probability that our random variable is less than or equal to k. Oh, so I did this wrong. So f of k, which is the probability that x is less than k. So if k is some roll of the dice, let's move this to the next page. So I have a little bit more room. So this is going to be the probability that our outcome is 1 plus the probability our outcome is 2, all the way up to the probability that the outcome is k. Right? So there's k terms here, and each of these probabilities is 1/6. And so we end up with a cumulative distribution function. F of k is k times 1/6. All right, so it's as straightforward as that. We often write our CDF as f of x equals the sum of y less than or equal to x of the probability, the PDF of y. So this is a connection between the PDF and the CDF, an important connection. Okay, so what we're going to use in the following discussion is we're going to use the PDFs. And we haven't thrown the term around a ton, but we've used the idea a lot when we've talked about histograms and relative frequency histograms, and those are just basically representations of PDFs. Let's talk about the mean of a random variable. Okay, so this is a measure of central tendency. And it's basically the average value of a random variable. So let's see. Let's just do a couple examples. Let's say x is the result of rolling a 4-sided die. Okay, so the tabular representation of the PDF would look like this. So each outcome has equal probability if it's a fair die. So what's the average value of the outcome of this random variable? Well, if you wanted to figure it out empirically, do lots of experiments. Okay, and then compute an average of the outcomes. Okay, that's kind of the connection here to average value. What we're going to do instead, and deal with this theoretically, is think of these as frequencies. A fourth of the time we get a 1, a fourth of the time we get a 2, a fourth of the time we get a 3, and a fourth of the time we get a 4. So on the long-term average is going to be this. A fourth of the time we get a 1, a fourth of the time we get a 2, a fourth of the time we get a 3, and a fourth of the time we get a 4. Okay, so this is 1/4 plus 2/4 plus 3/4 plus 4/4. And if you look at this, you'll see this is this can be simplified exactly to the average of all the values, and I'll come back to that. And what do we get? 4, 7, 8, 9, 10, 10 fourths, 5 halves. So that's the average value. Okay, so we would write mu of x is 5 halves, the mean of x. And if we look back here at the table, 5 halves we see is right here. Right, so I'm just going to put this in sort of symbolically. Right here is mu of x, right in the middle. And that's sort of what we expect to see for an average. So let's imagine the case when I don't have a fair four-sided die. Suppose the die is skewed. So the probability distribution function looks like this. So 1/10 of the time I get a 1, 3/10 of the time I get a 2, 4/10 I get a 3, and 2/10 I get a 4. So what's the mean of this random variable? Well, we're going to use the same idea right here. So mu is 0.1 times the outcome 1 plus 0.3 times the outcome 2 plus 0.4 times the outcome 3 plus 0.2 times the outcome 4. All right, so you work this out. And those are your sum ends, and you get the number 2.7. So here you see the average is skewed a little bit more towards 3 than the fair die, right? So the 2.5 was for the fair die. Here we're a little bit higher, 2.7. That's because there's more weight right here at the 3 and less down here, right? So it's like the weight has shifted over there. So I'm going to just try to indicate that the mean is shifted up a little bit. This formula here, this is called a weighted average. Okay, so mean is a weighted average. And the weights are the frequencies. So that's what the mean is. The mean is a weighted average where the weights are the frequencies. Mean is also referred to as the expected value of x. And so some books use mu to denote the mean. Some books will use mu with the random variable symbol as a subscript. And then some books use the bold E for expected value to denote the mu. Our stats textbook prefers this, so I'll try to stick with that where I can. Okay, so that's the mean. The mean is a weighted value. The idea of expected value is provocative in the sense that mu of x is the most likely outcome of x. That's one way to think about it. Okay, so the idea is that if you needed to bet on the outcome of a random variable and you only had one bet to make, calculate the mean, and that's most likely where the random variable is going to come out. And that's the motivation for the term expected value. That's the value we would expect on any one trial of the random variable x. Okay, so I'll leave mean there, It's basically the average you're used to with frequencies, or the weighted average. And the homework will have you do some examples of the mean. So let me give you the formal definition of the mean. So let x be a random variable. I'll be more specific. Let x be a discrete random variable with probability distribution function p of x. Then the mean of x is the sum over all the outcomes of x times the p of x. Okay? To show you that it really is just the average, consider the set of numbers 1, 2, 2, 3, 5, 5, 5, 7, and 9. Let's calculate the average of this. So what do we get? We get 1 plus 2 plus 2, that's 5, plus 3, that's 8, plus 10, that's 18, plus 7, that's 25, plus 5, that's 30, plus 9, that's 39. Okay, so the average equals 39 over the number of terms. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the average is 39 over 9. And so let's reduce that. What is that? 4 and 3, 4 and a third. But notice that this average, if you take the sum of all these things, and divide them by 9, so that's 1/9 plus 2/9, well, 2 times 2/9 plus 3/9 plus 3 times 5/9 plus 7/9 plus 9/9. Okay? Oops, but you can write this using frequencies. So here the frequencies, I guess I should put a 1 here. Here are the frequencies that each of the numbers occurred in our list, right? And so those are the weights. Well, frequencies are just another way to think of probabilities. So the average of a list of numbers that has repeated occurrences is the same thing as the weighted average using frequencies. Okay, and this would be how we think of a mean. Okay, if you infer a PDF from this. So the idea of average and the idea of mean are very closely related to one another. I alluded to this before in a previous example, but one of the ways that we interpret means is the center of a distribution. That's why mean, we associate it to central tendency. So here, if I have a plot of a PDF, the mean is going to be representing the middle somewhere. And so my visual guess would be the mean might be right about here. Okay. It's going to be pretty close to that tall bar. Okay. Mu of x Okay, there's other ways to talk about the central tendency of a distribution. The mean is just one of them. I alluded earlier to a couple other terms we'll see later. All right, central tendency, right, is just an estimation of the middle of a distribution. And then in Calc 2, in Calc we really talk about the continuous case. We talk about the centroid. As balance point. So in a way, a mu is telling us where this distribution will balance, and that's where frequency comes into play. Okay, so that's mean. Now let's talk about measuring spread of a random variable. Okay. We use the term variance to describe how a random variable spreads out. And in the picture to the right, we might have, so here's where we have the mean. Spread is how far the values of the random variable go on either side of the mean. So you can have a random variable that's really spread out, or you can have a random variable that's really concentrated. And what we're going to talk about here, the variance, gives us a measure of that spread. So the idea is measure how far the data is from the mean. Okay. So here our x are going to be in our sample space. And so x minus mu is the signed distance of x from mu. So if x is bigger than mu, then x minus mu is positive. If x is smaller than mu, x minus mu is going to be negative. But we don't want to mess around with the signs because signs can cause problems, unanticipated problems. So what we're going to be interested in is the squared distance. Okay, and this is always positive. And in statistics, we like squaring things. Okay, so x minus mu quantity squared, that's the squared distance of x from mu. And then what we're going to do is we're going to add all those things up. The sum of the squared distances. But because different x's appear with different frequencies, we're going to put those weights in there, the weights of their appearance. And so this is actually the formula for the mean of the squared distance. Right. So look at this. We've got these values of the squared distance. If you go back to the definition of mean here, if these x's are the squared distance, and the probabilities here are the frequencies of the x, then these probabilities here are the frequencies of these squared distances. So this is the mean of the squared distances. And in fact, this is the definition we take for variance. So I'll write that down here. So let x be a discrete random variable with PDF p of x. Then the variance of x is the sum over all the possible outcomes of the mean of the squared variance. Okay, I'm going to call it the variance of x. There's an alternative formula. So this is, you should regard this as a formula. You're going to use that to compute. There's an alternative formula And our stats textbook goes through the derivation, but it's the sum over the possible outcomes of x squared p of x, all minus mu squared. Okay, so implied that there's a parentheses there. So that's variation. It gives us a spread. We'll do an example of that in a minute. Then there's another thing I'm going to define while it's convenient, and that's the quantity called the standard deviation. Of x. Okay. And it's defined to be sigma. We use this lowercase Greek letter sigma, and it's the square root of the variance of x. So just a note on notation. The textbook likes to write the variance of x as sigma x squared, and it takes that as the definition of the symbol. You know, algebraically, they're exactly the same. But you know, some books like to take the definition of the variance as the symbolizing it with a sigma squared. I like writing my variance this way because it alludes to the idea that we can use functions or computers to calculate this stuff. All right, so let's do a couple examples, and we'll call it a screencast. So let's suppose we have our simple random variable with 4 outcomes, and here are the frequencies. Earlier we computed that the mu of this distribution was 2.7. So let's compute the variation, or the variance. Okay, so we'll use the formula that the variance is the mean of the squared distance. So here's the distance between 1 and mu, and then we square it, and then we multiply it by the frequency, and then do the same thing for the next term. The next term is outcome is 2, so the distance between 2 and mu is that. Square it and multiply it by the frequency. Next outcome is 3, so the distance between it and the mean is 3 minus 2.7. Square it, multiply by frequency. Okay, so that's the formula for variance. Crank this out. The term simplified to this. It's a real grind. And this is where we're thankful for computers, because they'll do these computations for us. You don't have to do them by hand. All right, so there's our variance. So if I draw a picture of our distribution, so we got 1, 2, 3, 4, and 1 is 0.1, 2 is 3 times taller than that, 3 is 4 times taller than the original, and 4 is twice as tall. We learned that mu is 2.7, so mu is about here. So let's draw that at 2.7. And now we have this variance is 1.14. So variance is a spread. And so 2.7 plus 1.14 is about 3.8. So here's the line mu plus sigma. And then subtract 1.15 from 2.7 and you get 1.5 something. Oh, that's sigma squared. Okay, that's the variance. So that's a good point. Let's figure out what the standard deviation is. So I'm going to throw this into R I have right here. The standard deviation is 1.071448. Okay, so the standard deviation is a little bit smaller. I'll use a blue. That's mu minus sigma. Yeah, so that should be a minus. Right. And then a mu plus sigma. Standard deviation is also a measure of spread. And in a way, standard deviation is preferred a little bit because when you're doing calculating variance, you've squared that distance. So in a way, taking the square root at the end undoes that. You know, it's not true. It doesn't undo it exactly. But insofar as you transformed your data with a squaring to do the calculation for variance, in some sense, taking the square root, at least from a unit sense, right? Here, if you've got a unit squared, taking the square root at the end takes that unit back to its regular or original measurement. So standard deviation is often used in preference to variance. And later we'll see that standard deviation has really important interpretations. You can kind of say with a lot of certainty how much of your data is between your mean minus 1 standard deviation and your mean plus 1 standard deviation. So I'm going to do two more examples and then give you a definition, and then we'll call it a screencast. I want to show you what happens if I switch these two values. So it's like switching these two columns. And so that's going to be pulling my data further away from the mean, at least on the left. And let's see what happens to the variance and the standard deviation. So my new PDF would look like this. My mu is going to be 2.5 if I go through that calculation. And the variance now is going to be 1 minus 2.5 squared times 0.3 plus 2 minus 2.5 squared times 0.1 plus 3 minus 2.5 squared times 0.4 plus 4 minus 2.5 squared times 0.2. Okay, that's the definition of variance. And if you go crunch this in a calculator or R, you get 1.25. Okay, notice this is larger than what we calculated before, like 1.14. And if I calculate the square root of this, we'll see that the standard deviation indeed is about 10% larger as well. Okay, so as I anticipated or alluded in my language, by swapping these columns, I pulled my data away from the mean, so that increased my measure of standard deviation or variance, showing that my data was spread out a little bit more. What I'll also point out to you is that if I were to draw a picture like this again, I would redraw these vertical lines and they'd be spread out in both directions, even though I only affected the spread on one side. Okay? But then again, it did shift my mean to the left a little bit. So one of the lessons of this type of thing is even if you make a real simple change in your data, like we did, we just swapped these two things, I had to recalculate all of these descriptive parameters for that new data set. Okay, let's do one more example. Let's look at the uniform distribution. Okay, so my PDF here is going to be the uniform distribution. So we calculated earlier, I think, or it's pretty clear that the mean for a uniform distribution here is going to be this number right in the middle. You can verify that, calculate the average. What about the variation? So what's the variation of this uniformly distributed random variable? Well, it's going to be 1 minus 2.5 squared times a fourth plus 2 minus 2.5 squared times a fourth. Oops. I can pull all those 1/4 out. And I get that. And let's just use a computer to calculate it. And I get my variance is 5/4. All right, and then take the square root of 5/4 to get the standard deviation, and I get 1.118. Okay, so the variation of x is 5/4 and the standard deviation is 1.118. So the PDF of a uniform distribution look like this. The mean is right here at 2.5 and the standard deviation brings us down about 1 unit. Okay, so this is an introduction to some important ways we describe random variables and discrete random variables in this case. Oh, well, let me mention the continuous case. Let's talk about the continuous case. So let x be a continuous random variable. Okay, then we talk about a probability mass function. Let p of x be a probability mass function. And so that means the probability that a random variable is falls between two numbers a and b, that equals the integral from a to b of p of x dx. And I described this in that handout. So we define mu of x, the mean, to be the integral of x p of x dx. And we define the variance to be the integral of x minus mu squared p of x dx. So essentially you should think of the summation becomes the integral. And the textbook would have us make these limits of integration infinite, but if you've got a finite interval over which your random variable is defined or the outcomes come out of, then these limits of integration become those finite limits. So we'll talk more about all this stuff this semester many times, but this idea of mean and variance and standard deviation are going to be really important to us as we head through the course. So I'll leave it there, and I will see you in class.